All right, let's get right into it. We're about to go on a pretty wild journey through the history of computing, from ancient clunky gears all the way to a technology so powerful it literally bends the rules of reality. Okay, just look at this number. It's kind of insane. That's a 9,000,000. It's a 1 followed by 30 zeros. And that is how much faster a new quantum computer is than the most powerful supercomputers we have today. This isn't just a little step up, it's a completely different league. So what does a nonillion actually mean in the real world? Well, think about it like this. A calculation that would take our absolute best classical supercomputer for 47,000 years to solve, a quantum chip can now do it in just a few minutes. It's the difference between a project that outlives entire civilizations and, the time it takes to brew a pot of coffee. That kind of power honestly feels like something straight out of science fiction, right? But to really get a handle on how we got to this quantum frontier, we have to look back. So how on earth did we get from counting on our fingers to this? Our journey starts way before silicon or electricity. It begins with metal, with gears and levers. This is the mechanical age, the very first glimmer of automated thinking. First up, let's just nail down a super simple definition. At its core, a computer is just any device that computes or calculates something to predict an outcome. By that logic, you could say we've had computers for a very, very long time. And I mean a long time. Over 2,000 years ago, the ancient Greeks built the Antikythera mechanism, an incredible device with 37 bronze gears just to predict eclipses. Fast forward almost 1,800 years, and you get Blaise Pascal with his mechanical adding machine. But the real visionary, the person who dreamt up the blueprint for every modern computer, that was Charles Babbage with his analytical engine. So why was everyone so obsessed with automating calculations? Well, because the stakes were life and death. Seriously, back in the 18th century, all the math for ship navigation was done by hand. One tiny mistake could lead to total disaster, like it did in 1707 when 4 warships crashed and 2,000 sailors died, all because of a navigation error. Babbage saw that human error was a huge threat, and he knew machines could fix it. And this is where the story takes a huge leap forward. Babbage's collaborator, a brilliant mind named Ada Lovelace, saw something nobody else did. She realized his machine wasn't just a number cruncher. She figured out it could be programmed to handle any kind of symbol, not just numbers. In writing the world's very first algorithm, she basically invented the entire concept of software. But let's be real, gears and levers can only take you so far. To get faster, we had to move from the physical world we can see to the invisible world of the electron. It was time for the electronic brain. Mechanical computers were amazing for their time, but they were also painfully slow, they were huge, and they broke down all the time. For the next big step, we needed something much faster and way more reliable. The answer, amazingly, came from the light bulb. Scientists figured out they could control the flow of electrons inside a glass vacuum tube. You can think of it like an electron faucet. By using a little grid, they could turn the stream of electrons on or off. And that simple on-off state? That's it. That's the physical version of the ones and zeros that are the foundation of all digital computing. This breakthrough led to absolute monsters like ENIAC, the first true electronic computer. And when I say monster, I mean it. It filled an entire room and used 18,000 of these vacuum tubes. Yeah, it was 1,000,000 times faster than a mechanical calculator, but it had a massive reliability problem. Just imagine having to find and replace 50 burnt-out light bulbs every single day just to keep your computer from crashing. Clearly, that wasn't going to work long-term. A solution was needed, and when it showed up in 1947, it changed everything. This next leap solved the heat and reliability problem and is the reason you have a supercomputer sitting in your pocket right now. Welcome to the Silicon Revolution. Back in 1947, scientists at Bell Labs invented something called the transistor. It did the exact same job as a vacuum tube. It was an electronic switch. But instead of being a big, fragile, hot glass bulb, it was tiny, solid, used way less power, and was incredibly reliable. This was a total game changer. And this wasn't just a simple upgrade, it kicked off an exponential race to the future. In 1965, a guy named Gordon Moore, one of the founders of Intel, noticed that the number of transistors we could cram onto a single chip was doubling about every 2 years. That observation, which we now call Moore's Law, became the relentless heartbeat of the entire tech industry for half a century. The result of this law is just staggering. The very first microprocessor back in 1970 had about 2,300 transistors. Today, a modern chip can have over 150,000 billion of them. It's just an unbelievable explosion in power, all thanks to our ability to shrink those transistors down smaller and smaller. And that miniaturization is why we went from ENIAC, a computer that took up an entire building, to the smartphone in your hand, which is millions of times more powerful. It's all thanks to cramming more and more transistors onto little slivers of silicon. But here's the catch with any exponential curve. Eventually, it has to flatten out. After 50 years of incredible, relentless progress, the silicon revolution is slamming into a fundamental physical wall. This is the end of an era, but it's also the beginning of something completely new. To put it bluntly, Moore's Law is dying. That steady, predictable doubling of power that has fueled our world for decades is grinding to a halt. And the reason isn't about money or manufacturing. It's about the laws of physics. We've now made transistors so ridiculously small, we're talking 3 nanometers, or the width of just 20 atoms, that the weird, spooky rules of quantum mechanics have started to mess things up. At that scale, electrons can literally just pass right through solid barriers. It's a phenomenon called quantum tunneling. This makes our on and off switches unreliable. The roads for electrons are just getting too narrow to work properly. So think back. The jump from gears to electrons gave us a mind-blowing increase in computing power. Now that the electronic path is reaching its end, what's the next fundamental force we can tap into to keep things moving forward? Well, the answer is to stop fighting against all this quantum weirdness and actually start using it. The next great leap in computing won't come from controlling electrons like simple light switches, but from harnessing the strange and incredibly powerful rules of quantum mechanics itself. And why do we need this new kind of computer? Because the universe, at its most basic level, is quantum. To accurately simulate even a pretty simple molecule like caffeine, a classical computer would need 10 to the power of 48 bits of information. That's a number so large it's almost meaningless. It's more bits than there are atoms on planet Earth. Our current computers just don't speak the language of reality. Quantum computers will. And this brings us full circle. We are standing on the edge of a new computing era, one that's going to be as different from our digital age as ours was from the age of gears. It leaves us with one final, incredible question. What secrets, from curing diseases to finding new worlds, will we finally unlock when our computers